Thank you. So, good afternoon, everybody. So, first of all, I would like to thank Robert, Serena, and the other organizers for this very kind invitation. It's my first time here in Vienna and here at the Institute also, and I'm really very much looking forward to this interesting meeting. So, I really, at the moment, I really enjoyed it a lot. So, since I learned today that yesterday was Jacob's birthday, so I really happy to join the best wishes for your birthday. So, the title of my talk is Exact Solution of Many Body Problems, and I have a disclaimer here, just to start. So I come from the community of numerical physics, and the word exact has a different flavor compared to, so for you probably it's more having some rigorous results. For us it's more finding a proper way to solve the many-body Schroedinger equation and keep errors under control. This is what we mean usually by exact. And so I will discuss exact methods, quantum Monte Carlo methods, and applications to ultracold atoms. I would like first to start by acknowledging some of the collaborations I had over the years, which contributed a lot to the results I will show you today, in particular the group in Barcelona, Jordi Boronat, Grigori Astrakarczyk, and Kim Kazulieras, then the University of Camerino with Sebastiano Pilati, and Luca Parisi, who was first was at the BEC Center and then he is at University of Newcastle. Let me start by saying that there are many quantum Monte Carlo methods, and here is a list that is not exhaustive. And so I just want to make sure that, okay, so that I will not talk about all possible quantum Monte Carlo methods, of course. So QMC methods can be divided into three groups. The first group is devoted to zero temperature, and so they look at the ground state of many body systems. And here probably the most versatile method and widely used is variational Monte Carlo, which is based on the variational principle, so finding an upper bound to the ground state energy using Monte Carlo methods just to do a multidimensional integral. Then there is diffusion Monte Carlo or projection method, and this is what I will be discussing during the talk mainly. And this solves exactly, in the sense that I was telling you before, the Schrödinger equation for a many-body system in the case of bosons. Then there is a path integral ground state, which is a mixed method between diffusion Monte Carlo and path integral, and has some disadvantages and advantages compared to diffusion Monte Carlo. And then concerning finite temperature, where the aim is to study the thermodynamics, we have, of course, path integral Monte Carlo, and then methods that are more applied to lattice systems, like auxiliary field Monte Carlo, which was used in the study of the attractive Hubbard model or the half-field repulsive Hubbard model. Then also there is another version of this method, which is the word line quantum Monte Carlo, which again applies to lattice models. A continuous time Monte Carlo, which solves the problem of the discreteness in imaginary time, which in the case of finite temperatures is related to the inverse temperature. And then there are other methods. So probably I should mention here diagrammatic Monte Carlo, which also is used at finite temperature and is a method which allows you to calculate to any order Feynman diagrams. And the third group of Monte Carlo methods deals instead with real-time dynamics. And here, practically all the methods are sort of variational in the sense that one wants to find a variational answer for the action. And this line of research is now getting a real large boost because of network, so the artificial intelligence network methods, which allow you to find a very good variational answer for the real-time variation. So there are important contributions recently by Carleo and other that really showed how one can solve real-time dynamics using this type of methods. Okay, so I will also discuss some history of quantum Monte Carlo methods looking at different things compared to what we heard this morning, but also in the community of quantum Monte Carlo, we have some very precise milestones which initiated in a way the field. So probably the first most influential paper was this paper by Macmillan back in 1965, who was concerned with the application of variational Monte Carlo to calculate the ground state of liquid helium. Here one starts with the microscopic Hamiltonian, which is exactly the same that you are using in your studies. And here the potential is is a Lennard-Jones potential with the proper parameters for helium-4. So this is the range of the interaction, which is on the order of few angstroms, and this is the depth of the well. And then what Macmillan did was use this Hamiltonian in a variational approach. So he calculated the expectation value of the Hamiltonian on this many body wave function psi, and he did it with variational Monte Carlo. So you can express the average, the ground state expectation value of the Hamiltonian in terms of a probability distribution, which then one can sample using the Metropolis algorithm. And so one finally calculates this quantity here that is called the local energy as a function of the n-dimensional or a 3n-dimensional, in this case, vector Rn, which collects the coordinates of all the particles. And by having a large enough sample, one can estimate the energy E. And so the crucial ingredients here are the choice of the wave function. And the choice was a Jastrow decomposition in terms of pairs. And he had a very simple expression for this Jastrow term, which depended on two variational parameters, A1 and A2. And here were the results for different values of A2, this exponent here. By changing A1, he got curves like this. And then, for example, he could say that this was the best value that he obtained for the ground state energy. And you see that the value is, so it's, of course, is an upper bound because it's a variational principle. But so it's not so far from the true ground state energy that is obtained in experiments. Okay, so this was the first very important paper where Monte Carlo methods were applied to many boson problems. Then there is this, 10 years later, came this paper by Kalosh, Levesque, and Verlet on using projection Monte Carlo, diffusion Monte Carlo, which in principle is exact, and using different two-body potentials like hard spheres, and then also other forces like the Aziz potential here. And they were able to show that you have a phase transition, a first-order phase transition from a fluid state of liquid helium and a crystal phase, so a solid phase, as you increase the density going in this direction. And then here, so concerning the liquid state, they could calculate the equation of state, and you see that now they have results that are in good agreement with experiments, and the discrepancy is now only due to the details of the potential. So the Aziz potential is a slightly modified Lennard-Jones potential, and by changing slightly parameters, you get a result that is slightly above or slightly above the experiments. So it's clear that with this method, they could calculate the ground state energy of a many-body system. The third very important contribution to the field came in 1980, and is again using projection Monte Carlo for fermions now, using the fixed node approximation. And this was a contribution by David Sepperly and Alder. And they calculated the ground state of Gellium, which is the model of electrons immersed in a uniform distribution of positive charge. And they could see that, for example, you have a transition from a paramagnetic to a ferromagnetic state by increasing this parameter Rs, that is the inverse density. So going in this direction, the density is reduced. And then they have also a transition from a fluid to a crystal, which in the case of electrons is the Wigner crystal. Okay? So this was, again, a very important contribution. Of course, this is not exact because it's based on the fixed node approximation, because for fermions, you know that in Monte Carlo you have the infamous sign problem, which does not allow you to get an exact result. But this was a very important contribution. So what I will discuss is, first of all, I will concentrate on projection Monte Carlo, and I will discuss what are the main features of the method. And then I will show you some applications to ultracold atoms. One is the equation of state of a dilute gas of bosons, which ties quite well with what we heard this morning. And then I will instead, as a second application, discuss mixtures of one-dimensional Bose gases, where for the single component, we know that the equation of state is can be calculated exactly, and this is the Lieb-Liniger model, which is the famous model in one dimension. But then one can make the model more complicated, including having, instead of just one component, two components. And so one can discuss repulsive mixtures where the two components have a repulsive interaction, and so you have the problem of phase separation, or attractive mixtures where you have an attraction between the two. And here there is a gas to liquid transition at zero temperature. Finally, if I have time, I will also discuss the polaron problem, so the single impurity in a quantum bath, and the possibility of having a formation of bipolarons, so a bound state of the two impurities. Okay? So let's go on. So what is projection Monte Carlo, or diffusion Monte Carlo? The main idea is that you start from the Schroedinger equation in imaginary time. So time is now IT divided by h bar. And then you have, this is the Schroedinger equation with some reference energy. And so the time evolution, of course, is given by the time evolution operator acting on the state at 0 time. So if at the initial time the state psi naught is not orthogonal to the ground state, then you can expand the wave function at the initial time in terms of the exact eigenstates of the Hamiltonian. And so for larger times, then you just apply the time evolution operator to the states psi n, and you get the corresponding energy En. And so if time is large, of course, the main contribution will come from the lowest states, n equals 0, okay? And so, and even more so, if you choose your reference energy to cancel exactly E naught, then you have that at large times, the time evolved wave function is proportional to the true ground state of the system. So this is the main idea. Okay? So it's just a projection in imaginary time. Okay, but then, so this is in principle, but then how one does it? And so there are two main ingredients. First of all, the algorithm is iterative, so you solve the time evolution for short time intervals, delta tau, okay, so then your wave function at time tau plus delta tau is related to the wave function at time tau by this time evolution. And the idea here is that if delta tau is small, you can use a Trotter decomposition. And so you can write this operator in terms of the potential energy. So if H is T plus B, so kinetic energy plus interaction energy. Interaction energy is diagonal in the coordinate representation. And so here you have the potential energy. And here you are left with the evolution of the kinetic energy operator. So, of course, this is exact if delta tau goes to 0, but the problem is that this calculation is undoable because you have here a quantity that fluctuates a lot. If you just change the configuration from R to another point, this contribution here can change, fluctuate widely. And so this gives you a normalization that changes very rapidly and wildly, and so makes the calculation untractable. So the way out is that you use importance sampling. So you use a guiding function, and so you don't solve for psi, but you solve for the product of psi times this, it's called a trial function that does not depend on time. And so your evolution is now in terms of f, and you have a new Green's function, which is the old Green's function here, multiplied by this factor that takes into account the difference in the trial function in position r and r prime. So the beauty here is that this new Green's function, g, can be written in terms of the action of an operator L that is called the Langevin operator, which is given here and contains the kinetic energy and the term that depends on the trial function. So you have a diffusion term given by this, and a drift term that is provided by your trial function. So moves the points in configuration space towards regions where the trial function is higher, is maximum, okay? And then, most importantly, the normalization term, which here was depending on the potential energy in R prime and R, now depends on the local energy, which the local energy is the same as was calculated in the variational calculation, and is a quantity that exhibits much smaller fluctuations compared to V of R. So this is the idea. And so finally, you solve for this, iteratively for this F, Okay, so you have a certain number of, they are called in our jargon walkers, so points in configuration space, which are distributed according to this function f, and you have a certain number of them that depends on time, okay? And so your distribution evolves from R prime to R according to diffusion, so which is given by this term here, drift, and branching. And the branching is provided by this exponential term. And so, and of course, this is what makes the normalization change during the evolution of your yeah. Yeah, so this I will tell you later. Okay, so in principle you have to you put in the trial function all the knowledge about the physics you have, and so then depending on the problem you choose different trial functions. But in principle the method does not care about the trial function, provided you have a time step small enough and the number of walkers large enough, then any trial function would give you to the same. So the only crucial point, the trial function must not be orthogonal to the ground state. Okay, so because in this case you miss the main term. Okay, right. Okay, so then you see the way the method, the algorithm works. You have a diffusion which allows walkers to explore the whole of configuration space, so guarantees ergodicity of your algorithm. Then you have the drift. Walkers are pushed where psi t is largest. So if you have a good trial wave function, then the algorithm is more efficient. But then you have branching, which tells you that these walkers are replicated according to some rule given here. And so the idea is that if you go to a region where the energy is low, then this walker will replicate. Okay? Instead, if you go to a region where the energy is too high, then the branching will kill the walkers. And here you see an example. No? So you start from a given configuration, then you do your diffusion and drift, you go to a new configuration, and then depending on this term here, the walker is killed, or the walker is generates one sun, or two suns, or any given number of suns. Okay, and so this is the mechanism that allows you to favorite walkers which enter a region where the local energy is minimum. Okay. And so you have systematic errors, of course. You have a time step error. Your delta tau has to be small enough. You have an error on the number of walkers. So you can prove that the method is exact only if your number of walkers is infinite. But then, of course, this means that has to be large enough. And then you have to check whether this bias is under control. But then after a long projection time, you have so your walkers will be distributed according to the product of the trial function times the true ground state of the system. And then you estimate the expectation value of the energy by calculating over the number of walkers the local energy, which means doing tests in terms of your probability distribution. But then since test is given by psi t times phi naught, you see that you have it here, and then psi t cancels, and you are left now with h calculated between psi t and phi naught. So since phi naught is the exact eigenstate, then you get the exact ground state energy, E naught. Okay, so this is how the method works. And then, of course, this is also a way that allows you to estimate what is the reference energy that you have to subtract here, okay? Because you can do this at the end of each iteration, And so this will be your reference energy here, which then allows you to have normalization that is stable in the process of the time evolution. Okay, so this is the essence of the method. Okay, so okay, so now I want to go to some applications, and as I said, first of all, I would like to discuss the equation of state of an interacting Bose gas. So it's exactly the model that we have seen this morning. So you start from the general microscopic Hamiltonian with some pairwise interaction. And here, for example, we used different interatomic potentials. We use the hard spheres, where so you have the potential is infinite below some range, and in this case, the scattering length is exactly the range of the interaction. So this is the solution of the two-body problem. Or we use the soft spheres with a different range R. And so here you can choose the height of the potential V naught in such a way that you have exactly the same scattering length as for the hard sphere problem. Okay, so you have, of course, the two-body problem can be solved analytically. This is how the scattering length depends on the range of the interaction and the height of the potential. So you can have two potentials that are different, but they have the same S-wave scattering length. So this is the idea. And for example, yeah, as I said, here, since the system is finally dilute, a good choice for your trial function is to put here, so you choose a Jastrow type of wave function, where this f is the solution of the two-body problem. Because in this way, you automatically include the effects of your short-range potential. Okay? And so you avoid the problem of having, for example, even if you solve the soft spheres problem, so you will have a discontinuity in the calculation of the potential energy every time two particles go from having a relative distance larger than capital R or smaller than capital R. While if you solve the two-body problem, your local energy is flat, okay? Because is the solution. So it's the solution of the two-body problem. Okay, and so, okay, so here are, so this is the famous equation of state that we have seen many times today, the mean field term, the Lieb-Liniger and the Wu correction. So this is valid, as we said, if NA cube is much smaller than 1. And as we also heard today, we know that microscopic details of the potential, such as the effective range of the potential, will enter only to higher order in higher order terms. So this expansion here is universal in the sense that whatever is your potential, provided they have the same scattering length, they should have the same equation of state. Okay. And okay, so here are the results. This is the case of hard spheres, where we consider the energy per particle as a function of NA cube. We see the mean field term that dominates at low density. Then we see a clear agreement with the Lieb-Liniger correction, while the Wu correction very rapidly gives you wrong results. And here we wanted to check universality. So we compare results for hard spheres and soft spheres, and we also subtracted the trivial mean field term. So here you see that all our points, so hard spheres and soft spheres with different ranges of the interaction, they all align along the Lieb-Liniger correction. So they provide the same equation of states, even though the potentials are completely different. And if we go to very low densities, so here is the 10 to the minus 6, 10 to the minus 5 range of Na cube, we see some evidence of the Wu correction. So we see that compared to the Lieb-Liniger, the Wu term would give you a lower energy, and our results seem to follow this. But this occurs only for very, very small values of Na cube, meaning that probably, so the constant under the logarithm here, which is model dependent, is relevant. And only if you go to very small values of Na cube, this term is evident in the equation of state. But what we see here is that you need to go to 10 to the minus 3 in the gas parameter to start seeing deviations from the universal curve. Okay. One can also calculate other observables like the pair correlation function. So this is the probability of finding two particles at some distance r. And we see here what happens for hard spheres for different values of Na cube. So, of course, if Na cube becomes large, like 10 to the minus 1, or so you start seeing shell effects. Okay, so the particles aggregate into shells. You are moving towards the solid. In the regime of dilute gas, Na cube 10 to the minus 4, here we have a clear picture of what universality means. Okay, because here you see the behavior of hard spheres, which is this solid line here as a function of the distance, and the behavior of soft spheres, which is this dashed line here. But in the region where the value of n times r cubed, so you are at a distance r where on average you have one particle per cube, which is this sets what is the mean interparticle distance between particles. You see that the two behave exactly in the same way. So if particles lie most of the time here, it doesn't matter what happens at short distances. Okay? So if the potential is hard spheres or soft spheres, they behave exactly in the same way. And this is a clear signature of the universality. By the way, here we show also the comparison with what you could calculate from Bogoliubov theory. So in Bogoliubov theory, you can calculate the Fourier transform of G of R, that is the static structure factor. And then you do the Fourier transform and you get G of R, and you get this line here, which in this region agrees with what we found for both hard spheres and soft spheres. We can also calculate the one-body density matrix. So the expectation value of the operator where you annihilate a particle at position 0 and you create it at position S. This is the famous result obtained by, I think it was separately for helium-4, where they calculated this quantity, and you can see here that when this saturates to an asymptotic value, of course, this is the condensate fraction. Okay, and so for helium, it is known that the condensate fraction is about 0.1 of the total density of the system. So you have the famous quantum depletion. In our case, we could calculate the same thing and compare it with the Bogoliubov quantum depletion. So what is the estimate of the number of particles outside the condensate within Bogoliubov theory, which, of course, within Bogoliubov theory has to be small, but we see that it agrees well with our results. And again, we see universality because different potentials give the same result for this condensate fraction. Only if you go to very large values of Na cube, then we see deviations from Bogoliubov, and of course, at large enough density, the condensate fraction goes to 0. Okay? Yeah, so this, you have seen it already this morning, so I just wanted to say that there is an experimental evidence of the Lee-Wan-Yang corrections to the equation of state. This was obtained in the group of Christophe Salomon in Paris, where they were using a Feshbach resonance to tune the S-wave scattering length. Okay, so they could make the scattering length larger, and they could see it from the cloud that by increasing the value of the scattering length, the cloud becomes larger and larger because of the repulsion, the extra repulsion. And they could measure in the center of the cloud, so in a region where you could say that the system is uniform, the grand canonical equation of state, so pressure versus chemical potential. And these are the results, the experimental results. They can really distinguish between the prediction of just mean field and mean field plus Lee-Wan-Yang. So this is a very clear experimental evidence of the correctness of the Lee-Wan-Yang term in the equation of state. They, of course, in principle, with this and with much more refined and precise measurements, they could, in principle, also see the Wu correction. Okay. Okay, that's all for the weakly interacting Bose gas in 3 dimensions. Now I want to go to a similar problem, but in 1 dimension. Okay, so we have a Bose gas in 1 dimension with contact interaction given by a delta function with a strength G. And this is known as the Lieb-Liniger model, or Lieb-Liniger Hamiltonian. Also here there are interesting milestones. So the first was Marvin Girardot, who realized that this Hamiltonian here, if G becomes very large and positive, you have an exact mapping between your bosons and fermions. Okay, so if you have hardcore bosons or impenetrable bosons, they behave as fermions because the infinite repulsion mimics the Pauli exclusion principle. So the equation of state of strongly repulsive bosons is the same as the equation of state of free fermions. Then Lieb and Liniger solved for exactly for the ground states and excitations using Bethe-Ansatz methods. And then lately, Yang and Yang managed to calculate exactly the thermodynamics of the same model. Okay? So here you have a single dimensionless parameter which involves the strength of the interaction and the density. And so if gamma is small, which means large density, this means weak coupling. Okay? And if gamma is large, which means small density, then you have strong coupling. So it's the opposite compared to what happens in 3D. So small density means a large interaction, and vice versa. And again, experiment-wise, so this, the crossover from the mean field regime to the strong coupling, which is also called the Tonks-Girardot gas, where you have the exact mapping, was seen in experiments. Here is a famous experiment where they measured the breathing mode of this cloud as a function of the strength of the parameter gamma. And they could compare with the theory that predicts different values of this breathing mode if you are in the mean field regime or in the Tonks-Girardot regime. They could follow the whole line. Okay, so this, I mean that this model is experimentally realizable. Okay, so here we do, we apply our QMC methods. And here again, the trial function is provided by a Jastrow factor. And here what is crucial is that the trial function also allows us to implement the proper interaction, okay? Because, of course, to simulate a delta function is not possible. But if we implement a trial function that contains exactly the exact condition for the delta function, that the derivative is discontinuous and is discontinuous by an amount proportional to g, then we can map our problem to the problem of non-interacting particles with a proper beta piles, as it is called, the boundary condition. And so this is the way we did it. And here are the results for the equation of state. This is the exact solution of the beta ansatz, the line, and we show that we can obtain exactly the results with the proper limits. And also by calculating the one-body density matrix, of course, in 1D, even at zero temperature, there is no Bose-Einstein condensation, and the one-body density matrix decays with a power law. And one can calculate using the theory of phonons what is the large Z behavior of the one-body density matrix, which decays with a power law, as I said, 1 over Z to some power nu. And this power nu depends on the interaction. So in particular, is 1/2 in the Tonks-Girardot limit or tends to 0 in the mean field. And our Monte Carlo calculation reproduces exactly the expected decay of the one-body density matrix. Okay, so we use this to calculate higher order correlation functions, but this is not what I want to discuss now, because I would like to move now to a more interesting problem, which is the problem of mixtures, where you now have a two-component gas, component 1 and component 2, which have a repulsive interaction modeled by the same delta interaction as before, but then you also have an interspecies interaction. So you have a G tilde, which is contact, but occurs between particles of component 1 and component 2. Okay? And so here we use, just for simplicity, that the two components have the same mass, you have contact interactions, you have the same intraspecies, and a different interspecies coupling, which could be either positive, and so you have a repulsive mixture, or could be negative, and you have an attractive mixture. And here you have two coupling constants, one related to G and one related to G tilde. So here again, you have some situations where this problem can be solved exactly. For example, it can be solved exactly if G is infinite. So if both components are in the Tonks-Girardot limit, for any G tilde, this is exactly solvable. But in other settings, it is not exactly solvable. Okay, so because it's not integrable if you have two different coupling constants. And here okay, so first of all, what one would expect from simple mean field theory at zero temperature. Of course, this is true for all mixtures, not just mixtures in 1D, but also in 1D. So here is the simple mean field energy functional for the mixture. You have so here I called G11 and G22. They have to be positive in order for the system to be mechanically stable. And the G12 can be either positive or negative. So this is the energy of just component 1, component 2, and this is the contribution at the level of mean field of the interspecies interaction. Of course, for the mixture to be miscible, you need to have that the compressibility must be positive. Okay, and so then this gives you a condition over the product of G11, G22, and G12. So this has to be larger than 0. If this is negative, instead, if G12 is positive, so you have a repulsion, then at the level of mean field, you would predict phase separation. The system phase separates, prefers to have all the atoms of component 1 on one side and atoms of component 2 on the other side. And instead, if G12 is negative, you have a collapse. Okay? So our question was we wanted to understand both the problem of phase separation and the problem of collapse. And okay, so in the case of repulsive mixtures, so phase separation, here we calculate the energy per particle as a function of polarization. So we can, in our Monte Carlo schema, we can decide how many particles we have in component 1 and component 2. And so we can plot the energy as a function of polarization. And here we do it for two values of gamma and different values of eta, which tells you what is the strength of the repulsion between the two components. Okay, so here we see that, for example, if eta is small, of course, we see a minimum at p equals 0. So the system prefers to be so to have no polarization. Okay, so polarization is 0. Same number of spin up and spin down, or same number of particles in component 1 and component 2. Instead, if eta exceeds the value of gamma, like here, eta equals 3, it's clear that the minimum is at polarization 1. So only one component is populated, the other component is 0. And the same occurs for larger values of gamma, but the change in behavior occurs at larger values of eta. So here we see that, of course, by increasing eta, this curve becomes flatter and flatter. And so from the second derivative, you can calculate the inverse compressibility, the inverse susceptibility in the case of spin. And we show it here, and we show that this diverges at the critical point, and the critical point is always when G tilde is equal to G. So we find that the same behavior predicted for mean field holds also for larger values of the interaction. So the phase separation occurs always when G tilde is equal to G. And this was not clear from the beginning. So it could be guessed from the behavior in mean field theory, where interaction is small, but was not clear what happens if you have a more strongly coupled gas. But our conclusion is that it occurs always when the two coupling constants are the same. And by the way, so here I show you the result, the comparison with the exact. So as I said, when gamma is infinite, so you are in the Tonks-Girardot limit, you have an exact solution, and our results agree well with the exact solution. And in this exact solution, there is no phase separation, because you would need that eta becomes infinite as well. And indeed, if you have two gases in the Tonks-Girardot limit, which means a two-component Fermi gas, with repulsion, the system is always in a miscible mixture. And this is the exact result that one can get from the Lieb-Liniger model. Okay, right. So how am I doing? 10 minutes more? Yeah, okay, so I should be fine. Now, what happens instead for attractive mixtures? So when eta is negative, so you have attraction between the two components. Here we see that we have a transition from a gas where the minimum exists at 0 density and a liquid. So here I show you the behavior of the density for different values of the ratio G tilde over G. So if the ratio is small, 0.3, these are the results, and you see that here the minimum is at 0 density. So the system is a gas. So if it prefers to have the lowest possible density. But then by increasing the ratio G tilde over G, suddenly a minimum appears at finite density, which tells you that the system prefers to have a very specific density and so form bubbles and have a gas to liquid transition. And here we could sketch the phase diagram in terms of the transition from liquid to gas. Here is the region where the system is unstable, so compressibility turns negative. And here is the line of the minimum density. So the minimum density shifts according to the ratio G tilde over G. Okay? And again, so this was something that was also predicted using an extension of the Gross-Pitayevsky equation, including beyond mean field terms, is the famous Petrov paper in 2015, where he predicted the existence of quantum droplets. Okay? In one dimension, they have not yet been seen experimentally, but they have been seen in 3 dimensions. So the formation of droplets due to beyond mean field terms in the equation of state. Okay, let me now go to something that I've seen that will be discussed also here, the Polaron problem, which is a very trendy subject nowadays in cold atoms, because it's one of the simplest systems, many-body systems, where you have a bath of which you know almost everything, and then you have a single impurity. And so then the question is how the properties of the impurity are changed due to the bath, and how the impurity changes the properties of the bath. Okay, so this is and usually, so it's very nice because one can, in ultra-cold atoms, compared to what was known in the case of solid-state physics, one can tune the interaction between the impurity and the bath at will. And so one can really see what are the effects of the interaction. So the Bose-Polaron problem was started by, in a famous paper by Landau and Pecker, who was interested in the effective mass of a polaron, how the mass of the impurities changed due to interaction with the bath. Okay, and and was important for the concept of quasi-particle. So a particle dressed by the excitations in the bath. In the case of the Landau-Pecker paper, of course, he was interested in an electron moving in a crystal. And so the impurity is interacting with the excitations of the crystal that are the phonons. In the case of the Bose-Polaron, you have an impurity interacting with the excitations of the Bose gas that are the Bogolyubov excitations. Okay, so you have an exact mapping between the 2 problems. In theory, you predict the existence of a repulsive branch and an attractive branch. So the repulsive branch is when the polaron, the impurity interacts repulsively with the medium, and the attractive branch where you have attraction. Okay, and what is nice is that again in ultra-cold atoms you can scan the whole phase diagram by changing the S-wave scattering length via a Feshbach resonance. And so both the repulsive branch and the attractive branch were measured, and okay, so here are the typical type of experiments, ejection spectroscopy, and okay, so they can compare directly with what theory provides. And okay, so our interest was besides the three-dimensional problem, also the one-dimensional problem, which is also very simple. Okay, so you have again the Lieb-Liniger Hamiltonian, now with just one impurity which interacts with some GBI. Okay, so you have again gamma with describes the bath, and then the parameter eta that describes the interaction between the impurity and the bath. Here again, okay, yeah. Again, here there is an exact solution. If gamma is infinite, so if the bath is a Fermi gas or a Tonks-Girardot gas, then there is an exact solution due to, I don't remember now the name. So it was a paper back in the late 60s, which gives you the energy of the impurity as a function of the interaction between the impurity and the bath. And here are the solid line, this pink solid line, this solid line here. And our results again match exactly with the exact results in the case of gamma infinity. But then, of course, if gamma is not infinity, then the energy of the impurity changes with eta and is different compared to the exact solution, and we can calculate exactly what is the energy, both in the case of repulsive impurity and attractive impurity. And also, we could calculate the effective mass, which means if the impurity moves, what will be its effective mass? Okay, and so this relates nicely with the paper of Landau and Pekar, because we could calculate what is the effect of the bath to the effective mass of the impurity. And here we see, again, there is an exact solution in the case of gamma infinity. In this case, the effective mass for attractive eta goes to 1/2, because in this case, you have the formation of a dimer, and then the dimer has twice the mass of the impurity, and so m over m star is 1/2. On the other side, if eta is infinite, then the effective mass goes to infinite, or its inverse goes to 0, because of course, if the particles are impenetrable and the impurity is also impenetrable, in order to move it has to move the whole system. And so if the system is infinite, then this goes to, the effective mass goes to infinity, or the inverse goes to 0. But if gamma is not infinite, so we have the help of the perturbation theory, which is valid if eta is small, but then it doesn't tell you what happens for large eta. And so here we see that according to the value of gamma, we have that the effective mass can become very large, and so you are moving towards this localization regime of the impurity, that the impurity is so heavy that it hardly moves. Okay? And there are evidences in experiments of large effective mass in an experiment where you have potassium atoms in a 1D gas of rubidium. I think I'm almost done. If maybe 1 minute, okay. So I just would like to sketch a problem that we are considering at the moment, and this is the bipolaron formation. So you have a one-dimensional Fermi gas or a Tonks-Girardot limit, and two impurities with the same mass and tunable interactions. So this is important because the idea is that so you have a bath that is, in this case, fermionic. You have the two impurities which they don't see each other, but they have a mediated interaction via the bath. Okay, and what we find that you can have the formation of a bound state of the two impurities. This is called the bipolaron, and has many important consequences in the field of superconductivity. So it's a very important problem. But what is nice is that you have also an exact solution here, because if the impurities are very heavy, so you can do a sort of Born-Oppenheimer approach where the two impurities are fixed, and then you have to calculate the energy of your Fermi gas in the presence of two impurities. And this is an exactly solvable problem. And you get a potential, which is shown here, that you can calculate for any value of the parameter eta, so the interaction between the impurity and the bath. And okay, so what you get is a potential that has an attractive part at short distance and then goes to zero at large distance. And then you can say, okay, so I have this potential, and then I use this effective potential to solve an effective Schrödinger equation and look for bound states. Okay? Okay, just to show you the last. Okay, so we did that, and then we, of course, in Monte Carlo, you can also calculate exactly what is the energy of the bipolaron, because this is given by the energy of the system plus the two impurities minus the energy of the bath minus twice the energy of the single polar. So if this quantity is below zero, then you can say that you have a bound state of the two impurities. And here is the energy of the single polaron, which is similar to what I've shown you before as a function of the mass ratio. And here the energy of the bipolaron as a function of the mass ratio. And indeed, for large mass ratios, we recover the results of the Born-Oppenheimer approximation, which is provided here. So I would like to stress here that this, even though is a fermionic calculation, is exact. There is no sign problem in one dimension, because in one dimension you know exactly where the nodes are, and so your quantum Monte Carlo calculation is exact. Okay, so just more applications. So we are now working at the polaron problem with two internal states and Rabi coupling, and then okay, so there is a whole list of things that one can do with projection Monte Carlo. And with this, I thank you for your attention. Thank you.